Hello everyone, we'll start the class now. So I welcome everyone to the week 4 Saturday session for the novel technologies for food processing and shelf life extension. So in this week we will be solving problems related to week 4 syllabus, which majorly includes food irradiation. Uh, so we'll start with the questions. If you guys have any doubts or if you want me to repeat any question, please unmute yourself or post it in the in-call messages. And if you want to answer any question also, you can either post it as a message or you can unmute yourself. Okay, so question 1, which among the following is a characteristic of a supercritical fluid? A, transport properties as that of a liquid. B, liquid like viscosity. C, gas like diffusivity. And D, positive surface tension. So before going into the question, do you guys know what a supercritical fluid is? You can either post it in the message or you can unmute yourself and answer. So what are the characteristics of a supercritical fluid? So if you look at a phase diagram here, where you have temperature in the x-axis and pressure in the y-axis, at a certain temperature called as Tc and at a certain temperature known as Pc, that is the critical pressure and the critical temperature, the liquid and gas are in equilibrium. They behave very identical. So after, above the Tc and above the Pc, here you can see there is a region known as the supercritical fluid. In this stage, the properties of the fluid will be intermediate between that of a liquid and a gas. So what happens in a supercritical fluid is that supercritical fluids like liquid will have very high solvent power. That is, it will be able to solubilize the solute very easily like that of a liquid, and it has very high density as that of a liquid. So the solvent power and the density is very similar to that of the liquid, whereas the other properties such as the viscosity, the diffusivity are all like the gas. So the supercritical fluid is kind of like the mixture of a liquid and a gas, and for a supercritical fluid the surface tension is also zero. So the one of the most important characteristic of a supercritical fluid is that the transport properties are in between liquid and gas. It is not either liquid, it is not either gas. It is in between liquid and a gas. It has a gas-like viscosity. That is, it has very low viscosity. It has a gas-like diffusivity, which is correct, and it has zero surface tension. Is this clear? What are the properties of the liquid and the gas in a supercritical fluid? The density and the solvent power is like liquid. The other properties like diffusivity, viscosity, and surface tension is like gas. So it has a gas-like diffusivity, and that is the right answer to this question. So the answer is option C. Any doubts in this? Any part that needs to be repeated? Okay, so since it has properties in between of liquid and gas, it is one of the upcoming modes of extraction, like supercritical fluids such as carbon dioxide is used in a lot of other techniques where you can easily recycle the carbon dioxide. You can have a very green process without much wastage, and it's a very energy efficient process as well. So using supercritical fluid as a solvent for extraction is now very up and coming in the food industries. Question 2, which of the following factors does not influence the power absorbed by the food in a microwave heating? A, frequency. B, electrical field strength. C, both frequency and electrical field strength. D, temperature. So what is the answer for this question? So what does the power absorbed by the food in the microwave depend upon? Do you guys know the formula for this? Okay, so a power consumed by the food in a microwave can be given as P is equal to 55.61 into 10 power minus 14, F, which stands for the frequency of the electromagnetic radiation given, E square, which stands for the electrical field strength, epsilon dash, which stands for the dielectric constant, and tan delta, which stands for the loss factor. So frequency and electric field strength is a very straightforward concept. So dielectric constant is the ability of the material to absorb the electromagnetic radiation. So you will be giving the electromagnetic radiation in a microwave unit, and because of that electromagnetic radiation, the atoms in the food will undergo some sort of stress. So it will have a molecular friction because of these electromagnetic radiation, and because of that friction, your food will start heating up. So dielectric constant is the ability of the material to absorb the electromagnetic radiation that you are giving. Whereas the loss factor, which stands for tan delta, is the ability of the material to dissipate the absorbed radiation into heat. So ideally, when you are trying to heat up a food, you would want the dielectric constant to be very high, so that it can absorb the electromagnetic radiation that you are giving. But your loss factor should be as low as possible, so that whatever it is getting absorbed is not dissipating away as some other processes. You want the system to heat up. uh, Apart from that, if the energy is being used up for some other processes, then it accounts for the loss factor. So you want a very low loss factor but a very high dielectric constant for any food that you are trying to heat up in a microwave. So power consumed by the food depends upon the frequency that you are giving, the electrical field strength, the dielectric constant, and the loss factor. So it does not depend upon the temperature of the food. So in this particular question, temperature is the factor that does not influence the power absorbed by the food. So the answer is option D. Is this clear? What is a dielectric constant and a loss factor? If you guys want me to repeat, you can let me know. So the dielectric constant is the ability to absorb the electromagnetic radiation, and tan delta, or the loss factor, is the ability of the material to dissipate whatever is absorbed. So you don't want it to dissipate, you want it to induce the friction and increase the temperature. So lower tan delta is preferred and higher epsilon dash is preferred. Hope this is clear. Okay, so moving to the next question. Okay, any doubt? One of you raised your hand. Any doubt? You can unmute yourself or post it in the message chat. Okay. So, identify the incorrect statement with respect to the microwave heating of foods. Shorter the frequency, higher is the penetration. The microwave absorption is directly proportional to the depth. See, the penetration depth of the microwave is inversely proportional to the loss tangent. And D, the thermal runaway results in non-uniform heating. So majority of this question can be answered by one single formula of the penetration depth. We'll look at the formula later on, but can you identify the incorrect statement in this? So what happens if the frequency is extremely low? Will the penetration be higher or lower? So when your frequency is sorry so when your frequency is low, your penetration will be high, because the depth of how much the microwaves are penetrating, that is the electromagnetic radiation is penetrating, is inversely proportional to that of the frequency. So your penetration depth is inversely proportional to frequency. So shorter the frequency, higher is the penetration. Okay, so moving on to the second statement, microwave heating absorption is directly proportional to depth. Is this true or false? So what happens when you have a food material that has a very less depth, and what will happen if you have a food material that has a very high depth? So anything that is getting absorbed. So when you're dealing with electromagnetic radiation and you're irradiating a food sample, the absorption will the energy that is transmitted throughout the food. Let's say you're having a rectangular slab kind of a food. You are subjecting the food to an electromagnetic radiation. So the intensity of the radiation will be highest at the surface where it is directly getting irradiated, and the intensity will keep on lowering as you go inside the food. That is, at the center of the food your radiation will be less, whereas at the surface the radiation will be more, which is very obvious. So your microwave absorption is not directly proportional to depth. In fact, it will keep on decreasing exponentially with depth. So if you have a 5 centimeter slab and if you have a 10 centimeter slab, the chances that your 5 centimeter slab will be radiated till the center is more. Whereas the bigger the food you're dealing with, the chances that even the center is getting irradiated is less. So you'll have a very exponential decay of the absorption that you can see. It will get irradiated most in the surface and least at the middle. So your microwave absorption decreases exponentially with depth, and hence it is not directly proportional. So this is the incorrect statement. And the penetration depth of a microwave is inversely proportional to the loss tangent. So if you have a lesser loss tangent was the ability of the material to dissipate whatever was absorbed. So if you have a good material that is not dissipating all the energy, then the depth to which this microwave can penetrate is more. So lesser the loss, more is the penetration depth. So penetration depth is inversely proportional to the loss tangent. And what is a thermal runway is that certain times when you keep some food inside the microwave, the already hot regions will become more hot, whereas the cold regions will remain colder. So this is because of something known as ionic conductance. So what happens in an ionic conductance is that it will start heating up the already hot area and will leave out the cold area. So this will result in non-uniform heating. And this process of a non-uniform heating is known as thermal runaway. So the answer is option B. That is, the microwave absorption decreases exponentially with depth and is not directly proportional. Hope this is clear. More concept on the thermal runway is given in the lecture videos. If you guys have any doubts also, you can ask. So question 4. The effects of irradiation treatment on food constituents can be minimized by A. Lowering of water content, B. Less anaerobic conditions, C. Increasing temperature, D. None of the above. Do you guys know what the answer is? You can take an example of a microwave, since that's pretty much there in almost everybody's house nowadays. You can figure out which one is more important: lowering of the water content, lesser anaerobic conditions, increasing the temperature, or none of the above. So one of the major reasons as to why we are irradiating a food constituent is to increase the temp. Yeah, the answer is lowering of water content. So the major reason as to why we are doing an irradiation is to I mean, it's for either for pasteurization or it's for sterilization. Basically, your first aim is to kill all the microorganisms that might result in food spoilage. So, but at the same time, it is also possible that your food constituents might start getting affected. So that you should have a process optimized in such a way that you'll be killing the microorganisms but not affecting your food constituents. So that should be your primary aim while designing any food process technique. So by lowering one of the main mechanism of irradiation induced sterilization is the formation of free radicals through water. So there are two mechanisms. Are you guys aware of that in case of irradiation? The first mechanism is that whatever rays you are passing through, gamma rays, beta rays, or anything, that will directly affect the macromolecule. It will cause breakage in the bonds or something of that sort. So it will directly affect the macromolecule. Or the second mechanism is by forming free radicals via water. So what will happen is if you are irradiating water, your water will start radiolyzing. That is, it will form other intermediates like excited water. You have free radicals such as OH minus ions. You have ionized water. So what all this does is this will introduce more free radicals into your food, and that will kind of affect sometimes your flavor and other properties as well. So you don't want water to get radiolyzed too much, but you want to kill the organisms. So the only way of doing that is by lowering the water content. So if you lower the water content, the amount of hydronium ions or excited water that you're forming will also be less. So that will not drastically affect your food constituents. So lowering of water content is actually the preferred way of going, because by that way you will have lesser radiolysis of water and lesser damage to the food constituents. And less anaerobic conditions is actually not preferred, because less anaerobic conditions means you're supplying oxygen, and oxygen will also form free radicals and will result in off flavors and odors. So you actually want to keep an anaerobic condition and not an aerobic condition. So you want low water, very less oxygen, and low temperature also, because if you lower the temperature, you will kind of immobilize the radicals that are formed. If you immobilize the radicals itself, the damage that it causes to the food will also reduce. So the way in which you will reduce the effects on the food constituents is by lowering the water content, lowering the amount of oxygen that is present, and lowering the amount of temperature. Hope this is clear. The answer is option A. If you increase the temperature, then yes, it might result in the microorganisms getting destroyed as well. But then that will also cause damage to your food constituents. So you don't want that. And if you increase the temperature also, your free radicals will start diffusing very rapidly, and you don't want that as well, because now then it will catalyze more reactions and it will damage the food more. So the answer is option A, lowering of the water content. Moving to question 5. Which among the following radiations has high linear energy transfer? So beta rays, alpha particles, protons, and both B and C, that is alpha particles and protons. So before we go in, do you guys know what is a linear energy transfer? It's not just B. B is the right answer. It's actually both alpha particles and protons. But why is it that alpha particles have a high LET? And what is an LET? So a linear energy transfer, or LET, is the average energy lost per unit distance of an ionizing particle. So when you're bombarding a food product with ionizing particles, there will be energy lost as it travels through the food particles. So there will be energy lost per unit distance. So more the energy lost, lesser distance it travels. Lesser the energy loss, more distance it travels. So it is inversely proportional. LET is inversely proportional to the penetration depth. Higher LET means lower penetration depth. Lower LET means higher penetration depth, because energy is not lost and it can actually travel through the food more. So, small beta rays are sparsely ionizing and have low LET values, whereas the common thing between alpha particles and protons are they are particulate radiations, that is, they are particles. Alpha particles have two positive charge, protons have a positive charge, so these are all very large particles that we are dealing with when compared to beta rays. So, since their mass is also higher, it is very densely ionizing and it has a very high LET as well. Generally, we see that higher the mass of the particles that you are ionizing, higher is the LET, which means lower is the penetration depth. If it is a higher mass, then it will start colliding with everything that it finds in the way and it will lose its energy quicker. Whereas if it is a very small particle like that of the beta rays or so, it will not collide with other particles a lot, and then this will result in a low LET, that is, it can penetrate more. Whereas larger or heavier particles will start hitting each other and will collide with other atoms and molecules, and hence it has a higher LET, that is, the energy loss is more. Hope this is clear. So both alpha particles and protons is the answer. So answer is option D. Any doubts as to why protons and alpha particles have high LET? Okay. Moving to question 6. Calculate the dissipation constant for a material which has a dielectric loss factor 15 and dielectric constant 65. So here the dissipation constant is also known as the loss factor that we discussed in one of the previous slides. So another name for the loss factor is dissipation constant. So do you guys know the relation between the dissipation constant, the dielectric loss factor and the dielectric constant? Or do you guys know how to solve, how to go about this question? Okay, so the dissipation constant for material can be given by epsilon double dash, which is the dielectric loss factor, and epsilon dash, which is the dielectric constant, and tan delta is the loss factor or the dissipation constant. So we already know what is the dielectric loss factor, which is the epsilon double dash, and epsilon dash is the dielectric constant given here as 65. So from there you can calculate tan delta, which is very straightforward. So 15 is equal to 65 into tan delta. So tan delta is 0.23. So this is your loss factor or your dissipation constant. So the answer is option B. Any doubt? Okay. So moving to question 7. Match the following. First, radioization, cobalt 60 electron beams and eliminating virus contamination. And in the other column, you have low penetrating power, 1 to 10 kilo. Sorry, yeah. So 1 to 10 kilo. Okay, dose limits and half life of 5.27 years, and then 10 to 100 you have kilohertz. So any clue what the answer is? So we'll start with radioization. What is the radioization? So there are three different procedures of food irradiation. One is rapportization, radioization, and radicidation. This was covered in, I think, lecture 14. So rapportization involves irradiating the food with extremely very high doses. And radioization is a medium dose, and radicidation, radicidation is a low dose. So according to the kind of dose that you're giving, your final purpose will also change. So when you're giving a very high dose, you're trying to sterilize all the bacteria and the viruses. When you're giving a medium dose, you're trying to delay food ripening, insect infestation and all. And when you're giving a very low dose, you're just trying to kill most of the food spoilage organisms. Okay, yeah, the answer is option B. So we'll start with one each this thing. So radioization uh, is the process where you'll give a medium dose, and that corresponds to 1 to 10 kilograms. So radioization is a medium dose which will kill 90% of the organisms and is used for preventing insect infestation, vegetable sprouting, fruit ripening and such so on. So radioization is the medium dose of irradiation that you give. And cobalt 60 is one of the source that is used for irradiation and has a half-life of 5.27 years. So 2 corresponds to C. And electron beams have low penetration power and high efficiency. And fourth, eliminating the virus contamination requires the highest dose possible, which is 10 to 100 kilograms. So this will somewhere correspond to approximately your rapidization. So rapidization is where you will kill the viruses, radioization is where you will kill the insects, and radicidation is where you will kill the food spoilage organisms like salmonella and such. The answer is option B. Okay. Moving on to question 8. The addition of radio frequency unit to the end of a conventional baking line causes A. the development of desired crumb structure and color, B. decrease in product yield, C. non-uniform moisture profile, and D. decrease in oven line speed. So any clue what the answer is? So what happens when you have a radio frequency unit at the end of the baking line? Is it preferred or not? Okay, so often industries prefer to have a radio frequency no, it's actually preferred to have a radio frequency unit at the end of the conventional baking line, because what in a radio frequency unit does is you will keep the food in between two electrodes and you will pass radio frequency waves which will heat up the it will heat up your food sample. So because of this heating up of the food sample after the baking line, so you have a combination of both thermal effect and a radio frequency effect. So what will happen is you will have a very uniform moisture profile generated, and because of this uniform moisture profile, it will be very easy to figure out how your consistency of your dough is, or consistency of your baked product is, and accordingly you can develop a desired crumb structure and color. So when you know how is the moisture profile of your food sample, it is very easy to follow the rest of the baking processes. And adding a radio frequency will ensure that it has a uniform moisture profile, and because of that you will have a desired crumb structure. And since radio frequency does not affect your food qualities much, it is mostly involved in drying processes or killing the microorganisms and such, it will not affect your food color, it will not affect your food odor and anything. So it is actually preferred to be having a radio frequency at the end of the baking line. So the RF dryer has proven to be effective because it produces, you can control the moisture content accurately. It will have a very uniform moisture profile, and this will add benefits to both the productivity and the quality. And it will not affect the color or your crumb structure of the baked item that you have. So without affecting your food constituents, it will be able to dry the food and have a uniform moisture profile. So the answer is option A. Moving to question 9. The dielectric constant and the loss tangent at a microwave frequency of 2450 megahertz and 30 degrees Celsius are 63 and 0.24 respectively. Determine the attenuation factor and the half power depth of the penetration using the Lambert's law of power absorption. So any clue how to proceed with this? So I don't think this is actually covered in one of your video lectures, but this was a part of your previous year assignments and all. So given the frequency is 2450 megahertz, temperature is 30 degrees Celsius, and your dielectric constant is given as 63, which is epsilon dash, and loss tangent is tan delta. Loss factor, loss tangent are all the same. So loss tangent is tan delta, which is equal to 0.24. So the attenuation factor, which will give you an idea of how the energy is dissipated in the energy profile is dissipated inside the food. The attenuation factor can be given by alpha dash, which is your attenuation factor, is equal to 2 pi by lambda epsilon dash by 2 into 1 plus tan square delta minus 1 the whole raised to half. So this formula, I'm not very sure if it is discussed in the video lectures, but this was a part of your previous year assignments. So you have your epsilon dash, you have tan delta. We need to find the wavelength. So you have the frequency here. So from the frequency, you can find out what is the wavelength. So your wavelength can be given as c by f, where c stands for the speed of light and f stands for the frequency. So I think this is a very common equation that you guys might be aware of since high school. So lambda is equal to c by f. So that's what you're substituting here. So when you start substituting the values, 2 pi into 2450, since it's in megahertz, you're multiplying by into 10 power 6. And c is given in meter per second, which is 3 into 10 power 8. And substituting the dielectric constant as 63 divided by 2 into 1 plus 0.24, which is your tan delta, 0.24 square minus 1, the whole power half. So when you solve this equation, you get 51.29 into 0.946. So your attenuation factor comes out to be 48.506 meter inverse. Any doubts in this part? Do you guys want me to go slow, or are you guys solving it? So the formulas and this particular PowerPoint will be available in the portal. You can access it anytime you want, and you can access the video also soon. It will be uploaded in the YouTube, and it will also be available in the portal. Okay, so we know what we have found out what is the attenuation factor, and penetration depth is stated in terms of half power depth. That is, the microwave power is reduced to 1/2 of the incident power. So as I had mentioned in the previous slides, your microwave power will kind of exponentially decay with respect to depth. It will not be the same as that it is in the surface. So your surface will have the highest power, which is the incident power, and as you go inside the food depth, the power will keep on dissipating and will go low. So your penetration, your half power depth is the depth at which your power is reduced to 1/2 of the incident power, which means your power P is equal to P naught by 2. So let's say this is the formula. Ln of P by P naught is equal to minus 2 alpha dash D. So P is the power at a certain depth, say D. P naught is the incident power that was initially given. Alpha dash is the attenuation factor, and D is your penetration depth. So when you're dealing with half power depth, it means that your power has reduced to 1/2 of the incident power, which means P is now equal to 1/2 of P naught. Is this clear? Only when we're dealing with half power depth, not the normal equation. The normal equation is this, but when you mean that you have to calculate the half power depth, it means that power has now reduced to 1/2 of the incident power. So only in this condition, P is equal to half of P naught. So you substitute that half of P naught is equal to minus 2 alpha dash D, and P naught gets cancelled. So you have ln of 2, that is minus ln of half, which is 0.693, divided by 2 alpha dash, which is equal to your half power depth. This is half power depth. So now since you've calculated your attenuation factor, you substitute it in this equation, which is 0.693 divided by 2 into 48.5, and this will give you your half power depth of 0.0071 meters or 7.1 millimeter. So is this derivation clear? How to figure out the half power depth? Any doubts, any part of this question that needs to be repeated? So when it is asked, just find out the penetration depth, and if you know what is P and P naught, you just directly substitute the values and find out D here. When it is asked half power depth, it means it is half the power of the initial incident power. So then at that time you substitute 1/2 of P naught, and ln of 2 is 0.693, and you have 2 alpha dash that is coming to this side, and when you substitute the attenuation factor here, okay, we'll from the beginning, is it? Okay, we'll start from the beginning. So the attenuation factor can tell you how is the energy profile inside the yeah, anybody else raise the hands? Do you want me to repeat the question? Okay, so the attenuation factor will tell you kind of how the energy is being dissipated inside the food particle that is being irradiated. So the attenuation factor's equation can be given by alpha dash is equal to 2 pi by lambda epsilon dash by 2 into 1 plus tan square delta minus 1 the whole half. So here lambda stands for the wavelength of your microwave, epsilon dash stands for your dielectric constant, tan delta stands for your loss factor. So we have all the parameters, we are just going to substitute, except that microwave frequency is given, we have to calculate the microwave wavelength. So do you guys understand how to calculate wavelength from frequency? Is that part clear? So wavelength is equal to speed of light, c by frequency. That is what I am substituting here. So c by frequency is wavelength, and you have the rest of the formula coming directly just like that. And now that we have all the parameters here, I am just substituting it in the proper SI units. So 2 pi into 2450 megahertz is what is given. So megahertz I am converting into hertz. So into 10 power 6. Speed of light is 3 into 10 power 8 meter per second. Epsilon dash, which is the dielectric constant, I am substituting it as 63. Tan delta is 0.24. So you are asked to square it. So 0.24 the whole square minus 1 the whole raised to half. So I hope this part is clear. So alpha dash is now equal to, I am just simplifying this. So this one corresponds to 51.29 and this corresponds somewhere around 0.9. So I just simplified it and wrote the numericals. So you get 51.29 and 0.946 inside the bracket. So when you multiply it, it comes out 48.506 meter inverse. So this is your attenuation factor. So this is what was asked inside the question. You have to calculate the attenuation factor and you have to calculate something known as the half power depth of penetration. So as we discussed in the previous slides, when you irradiate a food sample with a microwave, you will have incident light at the surface, which is the maximum, and then as the microwave starts penetrating inside the food, its energy will be lost slowly. So what is there, the energy that is there in the surface will not be the same energy at some other depth of the food, because energy is continuously being lost as it travels inside the food. Is this part clear? Why is there an energy loss and all? The microwave absorption dissipates exponentially less. So microwave absorption keeps on decreasing with depth. So what you have in, what you send initially and what the food receives at the center might not be the same, because energy is being continuously lost. So penetration depth is basically the amount of the depth in the food till which you can feel the microwave intensity. Let's say if your microwave intensity is able to travel 5 centimeters, then penetration depth is actually 5 centimeters. That's what it means. How much the microwave is penetrating inside the food. And when you mean half power depth, it means at certain point inside the food, your power will be half of what you initially sent. Is this clear? Let's say you have a 50 centimeter food block. At somewhere at around 10 centimeter, let's say your power has dissipated half. You sent some amount watts of power, and now the power has become half of that what you sent at 10 centimeters. I'm just giving an example. I'm not saying that the answer is 10 centimeter. For example, at 10 centimeter, if your power has reduced to half, then that 10 centimeter is known as the half power depth. So at that 10 centimeters, your power P is equal to half of P naught. P naught being the incident power that you sent, or the initial power that you sent. So this is the formula for calculating power at any depth of the food. If you have 50 centimeter block, you can calculate what the power is at any point in the food particle. So if you want to calculate a 10 centimeter, you just substitute D as 10 centimeter, and if you have the other parameters, you can calculate what was the power at that centimeters. If you change it to 50 centimeter, you can calculate what is the power at 50 centimeters. So this gives a relation between your power and your depth. So half power depth is the power at which it becomes half of P naught. I hope this is clear now. So half power depth is where it becomes half of P naught. So you're substituting P as half of P naught. P naught gets cancelled, and you will have ln of half on this side. And alpha dash is what you calculated before, which is the attenuation factor. And you need to find out what is the half power depth, which is D here. So ln of half divided by minus 2 alpha will give you D. So ln of half divided by ln of half will come out to be minus 0.693. Minus gets cancelled here. So you'll have 0.693 divided by 2 alpha dash is equal to D. Is this clear or is it still confusing? This particular formula is only applicable for half power depth. This is applicable for the entire food material. I hope this is clear. So alpha dash you are substituting as 48.5. From there you calculate what is the half power depth, which is 7.1 millimeters. So the answer is option D. So I am uploading it as soon as possible. You guys, if you guys still have doubts, you can get back to me by mail or through the discussion forum that is there in the portal. So moving on to question 10. Which of the following microorganism is most sensitive to ionizing radiation? A. Bacillus cereus, B. Deinococcus radiodurans, C. Toxoplasma gondii, and D. Dipteran vidivirus. So what is the relation between the kind of organism and the sensitivity? Is there any trend that you guys are aware of? So in one of the lectures, it would have been explained that The more complex is your organism, more sensitive it is to ionizing radiation, which is why humans, being one of the most complex organisms, are very, very sensitive to X-rays and such. Whereas most simple organisms, like say bacteria and virus, are very, very resistant to X-rays. So the higher the complexity, more the sensitivity also. So when you're given multiple organisms, you need to figure out how is the complexity of the different organisms that you're dealing with. So here you can see virus is a kind of a virus, and viral particles are extremely simple organisms, and hence they are much more resistant to ionizing radiation. So, Dipteran virus is a virus species, and viruses are very resistant to irradiation and require very high doses used in commercial processing. Whereas the rest of the two organisms, let's look at Bacillus and Deinococcus. So, both Bacillus and Deinococcus are organisms that produce spores. So, after viruses, spore forming organisms are also very resistant because those spores will have a very thick coating which is not very easily broken by thermal processing or by radiation or so. The coat of the spore is so resistant that that makes the organism very resistant to the ionizing radiation as well. So after virus comes the spore forming organisms, which is Bacillus and Cereus. Bacillus and Deinococcus, sorry. And then after the spore forming organisms come the vegetative cells and non-spore forming bacteria. And finally come parasites and insects, which is Toxoplasma gondii. So Toxoplasma gondii is a kind of an insect or parasite, and it is inactivated at a much lower dose. So here you can see the trend, that is the virus is the most simple and is the most resistant. Then comes the spore forming bacteria such as Bacillus and Deinococcus. Then comes non-spore forming bacteria, and then comes insects and parasites. So insects and parasites require the least dose of ionizing radiation as they are most sensitive. So the answer is option C here, not D here. Sorry. So Toxoplasma gondii being a very complex organism amongst the other three, it is more sensitive to ionizing radiation. So the answer is option C. Hope this is clear. Which is why, if you guys remember in one of the previous slides, we were talking about rapidization, radioization and all. So in this case, rapidization, where you have very high doses of irradiation, that is the only technique that will clear out the viruses. Whereas the other low dose techniques will not clear out the viruses. This is because viruses are very simple bacteria, and they have a very strong coat as well, protein coat as well. So moving to question 11. What is the penetration depth of a microwave emitted at a frequency of 2450 megahertz in raw potatoes, which has a dielectric constant of 66 and loss tangent of 0.227? The speed of the wave may be taken as 3 into 10 power 8 meter per second. So any clue how to solve this? So one of the issues is that you cannot solve by the previous formula that we were looking at. Ln P by P naught equal to minus 2 alpha dash D cannot be solved because you do not know what the P is. We are not looking at half power depth here. We are looking at the normal penetration depth. So since we do not know D also, since we do not know P also, we cannot use that particular formula. So there is another formula for calculating the penetration depth. We look at that. So given here is the frequency, which is 2450 megahertz. We have the dielectric constant as 66 and your loss tangent or loss factor as 0.227. So the penetration depth in this case, when you do not know the power at a certain point, you can calculate the penetration depth via this formula. X is equal to lambda divided by 2 pi epsilon dash tan delta. Is it clear why we are not using the previous formula? We do not know P, we do not know D. And we have to calculate the attenuation factor also, which is not known. Which is why we are using this particular formula, which is more straightforward. And this is for the normal penetration depth. This is not the half penetration depth also. Hope this is clear. So again, lambda can be given as C by F. So lambda is equal to 3 into 10 power 8, and frequency is given as 2450 megahertz, which is 2450 into 10 power 6 hertz. So your wavelength of the microwave that you are emitting is 0.122 meters. So now this you can substitute back inside this particular equation. You already know what is epsilon dash and tan delta, and it's a straightforward substitution and calculation. So you're substituting lambda as 0.122, your epsilon dash as 66, and tan delta as 0.227. If you calculate, x comes out to be 5.02 into 10 power minus 3 meters, which is 5 millimeters. So the answer is option A. Is this clear? So try to use this formula when asked for penetration depth. When used for half penetration depth, you can use the other formula given in the previous slide. Okay, moving on to question 12. Which among the following is the correct order of sensitivity of water-soluble vitamins to irradiation? So you have a difference of ascorbic acid, pyridoxine, thiamine, riboflavin, folic acid. So any clue which one is the most sensitive? Okay, so which one is more resistant to irradiation? Water soluble vitamins or fat soluble vitamins? So what happens when you irradiate water soluble vitamins? You will have the typical radiolysis of water happening. So if you irradiate any food sample, one of the mechanism is radiolysis of water. So if your water starts forming radicals and everything, it will start affecting the vitamins that is present, that's dissolved in that water. So all those free radicals will start damaging the vitamins, and hence that your vitamins will start degrading or be getting affected. Whereas in case of fat soluble vitamins, you will not have, your water content will be very less. So in that case, you're ruling out one of the mechanism of irradiation. That is, your water radiolysis is reduced, and hence your fat soluble vitamins are not that affected. Whereas water soluble vitamins, which are already present in water, will have the effect of water radiolysis and hence will get affected more. So your water soluble vitamins are more sensitive than your fat soluble vitamins because of water radiolysis. Hope this is clear. So amongst these, the extent of vitamin loss will depend upon, apart from just directly the kind of vitamins, we are also looking at the dose that the food receives and also the physical state of the food. So if you're dealing with a frozen food, then the effect will be less. But if you're dealing with a liquid food, then the effect will be more. So the physical state of the food will actually determine how much of the vitamin is lost. So the order of sensitivity as per the WHO reports and other studies have been shown that thiamine is most sensitive, followed by ascorbic acid, pyridoxine, riboflavin, and then folic acid. In fact, the degradation of thiamine is one kind of a test to figure out how much your food has been irradiated or how much your nutrient content has lost. It is often used as a kind of a test to figure out how much the food has any nutritional quality left. So this is for your water soluble vitamins, and this is according to the WHO. So in case of when you're dealing with fat soluble vitamins, the sensitivity is that vitamin E is most sensitive, followed by A, then D, and then K. So the answer to this is option B. And fat soluble vitamins are more resistant than water soluble vitamins. Any doubts? Moving to question 13. Which of the following packaging materials withstand the maximum dose of irradiation? A. Polyvinyl chloride, B. Polystyrene, B. Polypropylene, and D. Polyethylene. Any clue which one is the most strongest material, most preferred material in case of packaging in terms of resistance to irradiation? Okay, so the difference between polystyrene and polypropylene, polyethylene is that when you're dealing with propylene functional groups or ethylene functional groups, these are aliphatic functional groups. That is, you're dealing with CH2. Whereas polystyrene has a lot of benzene rings or aromatic rings rather. So when your packaging material has a lot of aromatic rings, they are generally found to be more resistant to irradiation. So if it is very rich in aromatic groups, it is more resistant. Whereas the packaging materials that have a lot of aliphatic groups are found to be slightly lesser resistant. And why PVC is not that resistant is because when you radiate the packaging material with more than what it can withstand, the chloride atoms will kind of start to undergo certain reactions that is not preferable. So the maximum dose that can be given to a PVC, a polystyrene, a polypropylene, polyethylene are 100 kilograms, 5000 kilograms, 25 kilograms and 1000 kilograms respectively. So here you can see the most preferred is polystyrene, followed by polyethylene, and then PVC, and then polypropylene. So polystyrene is most preferred because it is very rich in aromatic functional groups, and that kind of gives a resistance to irradiation. That is, the CC bonds, the carbon-carbon bonds that are formed in the aromatic rings are more difficult to break than your CH2 bonds. So because of this, the aromatic rings confer resistance to radiation. So the answer is option B. Hope this is clear. If you guys want me to repeat any question, kindly let me know. Question 14. The D10 for Listeria monocytogenes in meat is 0.75 kilograms. Calculate the radiation dose in kilograms needed to reduce the Listeria count by 8 log cycles. So before we go forward, do you guys remember what is a D10 value? It was discussed in the previous week. Okay, so when you're dealing with something like a D10, it is the value required to reduce the number of microorganisms by 1/10 of what was originally present. So if you have 80 microorganisms or 80 bacteria initially, and if you reduce it to 8, that is 1/10 of the initial value, then the amount of dose required for that reduction is known as D10. So the amount of dose that is required to reduce the number of microorganisms by 1/10 of its original value. So any microbial death kinetics is generally a first order kinetics, and it can be given as ln of n by n naught is equal to minus d by d naught, where n is the number of surviving microorganisms. That is, like after irradiation, how much microorganisms are still surviving. That is given by n. N naught is what was originally present before the radiation process. That is n naught. D is the dose that you gave in the irradiation process, and d naught is a constant that depends on the type of organisms. So d naught is a characteristic of the organism. N is the number that is surviving right now after the radiation. N naught was before the radiation, and D is the dosage that you are giving. So in order to incorporate the concept of D10, when you are dealing with D10, then N is equal to 1 by 10 of N naught. Is this clear? The dose value caused for the reduction of the number of surviving organisms by a factor of 10. So n is equal to 1 by 10 of n naught. So that is what we are going to substitute here. So if you substitute n is equal to 1 by 10 of n naught, so n naught will get cancelled. So you have ln of 1 by 10 in the LHS, and this is equal to d10. That is, that dose is corresponding, the dose is known as d10. So minus d10 divided by d naught. D naught is a constant for a microorganism, so that will not change. So that you can calculate what is d naught now. Since d naught is not given in this question, we need to in order to calculate this, in order to calculate the d that you have given, we need to first calculate what is d naught. Is this clear? So we know only the d10. We don't know what is the dose that we gave. So if we calculate what is n naught and d naught, we can calculate what is d. And when we mean 8 log cycles, it means this is equal to 8. Log cycles is number of log reductions. So if you mean it was reduced by 8 log cycles, then ln of n by n naught is equal to 8. That is what it means when you mean log cycles. If you mean 6 log cycles, then ln n by n naught is equal to 6. So it is the number of log cycles of reduction of the microorganisms after the radiation process. So now you are substituting d naught. D naught is equal to minus ln of 1 by 10 divided by d10. Sorry, d10 divided by ln of 1 by 10. D naught is equal to d10 divided by ln of 10. So that is what you are going to substitute in the first equation. So in this equation, you are substituting d naught, which is equal to minus d by d10 into ln of 10. Ln of 10 you are bringing to the LHS. So ln of n by n naught divided by ln of 10 is equal to minus d by d10. Is this clear? Any part that needs to be repeated again? What is d10 and all? I'm just calculating what is d naught in terms of d10 and substituting it back into the first equation. So bringing ln 10 to LHS, ln of n by n naught divided by ln of 10 is equal to minus d by d10. So if you guys remember the base change rule in natural logarithms, so the moment you have ln of the something divided by ln of something else, but the base is the same, you can automatically change this as your base. That is, now it will become ln of n by n naught to the base 10, which is nothing but log. This is the base change rule of logarithm. I hope this is clear. Any doubts in this step? How it became ln to log? Okay, so given in the equation, d10 is given as 0.75 kilograms and 8 log reduction cycles is what has happened. So log of n naught by n is given as 8. So you are substituting it in this equation. So log of n naught by n is 8. So n by n naught is minus 8. That is how you have a negative signature, negative sign here. So minus 8 is equal to minus d into divided by 0.75. So minus minus gets cancelled. You have d is equal to 8 into 0.75, which is 6 kilograms. So the answer is option C. Any doubt that any step that needs to be repeated? So even if you don't know the d naught of d naught of microorganism, if you know the d10, you can calculate d naught. So which part of it that needs to be repeated? Any doubts? So if you have the d naught, this is the relation that you will use. If you only have the d10 value, this is the relation that you will use. The derivation is not important. I just wrote it down so that you can understand where this came from. Okay, moving on to question 15. The half-life of radium is 1600 years. The fraction of a sample of radium remaining after 6400 years would be dash. So these kinds of problems we would have solved somewhere in high school as well. So, do you guys remember what is the half-life of a radioisotope? So, the half-life is the time taken for half of its radioactivity to be lost. So, that is known as the half-life. So, basically, your total time will be equal to so your T half will be at the time point where half of the radiation or the radioactivity of the substance is lost. So this is given by, for any general equation, is given as n is equal to n naught e power minus lambda t. So n here will be half, in case of a half life, half of the radioactivity is lost. So n will be equal to half of n naught. So you're substituting n as half of n naught. N naught gets cancelled. So and you have e power minus lambda t in this side, RHS. So if you take the negative sign and take a logarithm, so you'll have ln of 2 equal to lambda t half, which is your half life. Is this clear till here? So your t half given here is 1600 years. So you're just substituting, since we don't know what lambda is, we are given only the half life of the radium. We need to figure out what is n by n naught. That is the fraction of sample of radium remaining. So since we're dealing with fraction, they are asking what is n by n naught. They're not asking the amount of sample remaining, they're asking the fraction of sample remaining. So we need to calculate what is n by n naught. We have what is the time given, which is 6400 years, but we do not know what is the lambda, which is why we are calculating lambda first from the t half that is given. So lambda is ln of 2 divided by 1600. So this we'll substitute back in the same equation. So n is equal to n naught e power minus ln of 2 divided by 1600 into time that is asked in the question, which is 6400 years. So this is equal to 1600 into 4 is 6400. So this becomes minus 4 ln of 2, which is also equal to ln of 2 power minus 4. This is the one of the properties in logarithm. I hope this is something that you're familiar with. And since you have e power ln of 2 power minus 4, you can just directly bring whatever is there inside the logarithm term, which is 2 power minus 4. E power ln is the same as x. E power ln x is same as x. So this is n is equal to n naught into 2 power minus 4, which is equal to 1 by 16. So n by n naught is equal to 1 by 16. So 1 by 16 is the fraction of the radium that is left after 6400 years. So the answer is option D. Hope this is clear. So if you have only the half-life given, you can calculate the lambda from that, and lambda will remain constant for a particular material that you are dealing with. So you can substitute it back inside the original equation, and with the given time you can calculate what is the fraction remaining, which is 1/16 of the original that you had. Moving on to question 16. Which test is used to estimate the reduced viability of microorganisms in food after irradiation, that measures both the dead and alive microorganisms in conjunction with gram-negative bacteria count? So you have three tests that is given: Nimulus amoebocyte lysate test, B alkaline phosphatase test, C direct epifluorescent filter technique. So any clue what the answer is? Have you guys come across these tests before? Okay, so what is the characteristic feature of a gram-negative bacteria? Are you guys aware of that when compared to a gram-positive bacteria? So a gram-negative bacteria has, the answer is D. But any clue what? how they are used, how the tests are used. So so one of the characteristic of a gram-negative bacteria is that it has a cell wall. Outside the cell wall, it has something known as a lipopolysaccharide, which is known as the LPS. So that is the characteristic feature of a gram-negative bacteria, and that is what is exploited in this test. So in the limulus amoebocyte lysate test, also known as the LAL test, what is done is these LPS or cell wall of the gram-negative bacteria have the ability to gelate the blood cells of a crab known as limulus. So the blood cells of limulus crab are taken, and when you deal with a food that has a lot of gram-negative bacteria, the LPS present in the gram-negative bacteria will cause the gelation of the blood cells. So according to the amount of gelation that is present in your sample, you can directly figure out semi-quantitatively how much gram-negative bacteria was present inside the food. So more the gelation, more the gram-negative bacteria, because it had more LPS. So that is how LAL test is done. So LAL test will give you an idea of how much gram-negative bacteria was present. Whereas the alkaline phosphatase is an enzyme that is originally present in milk. But when you increase the temperature, like in case of pasteurization, when you're dealing with very high temperatures, this enzyme is denatured. So the enzyme is no longer active anymore. So this will tell you if your milk is properly pasteurized, this enzyme will not be active. Whereas if your milk is not properly pasteurized, or if it is been mixed with other raw milk, this will have some amount of alkaline phosphatase present, and that will give a certain result. So alkaline phosphatase test will give you if the pasteurization is successful or not. If your pasteurization is successful, your enzyme activity will not be there. If your pasteurization is unsuccessful, you will have alkaline phosphatase activity. Hope this is clear. And the third technique, which is the direct epifluorescent filter technique, what happens is that this was originally developed for milk samples. So your food samples are passed through a membrane, let's say for example a polycarbonate membrane or so, and all your microorganisms or all your gram-negative bacteria will be stuck onto the membrane. So when you stain this membrane with a stain known as an acridine orange and examine it under the fluorescent microscope, all your bacteria, that is your gram-negative bacteria and all, will take up the stain, whereas other things will not take up the stain. So your viable cells will take up your orange stain, and so more the orange stain present in the filter, more is the amount of bacteria. So you're passing your food through a membrane, you're staining the membrane and viewing it under the microscope. So if you find more orange cells in the microscope, it means there are more gram-negative bacteria present. So both LAL and the epifluorescent filter technique are techniques that is used to figure out how much bacteria is present inside the sample. So the answer is option D. Hope this is clear. Moving on to question 17. Calculate the thickness of the lead needed to absorb 99.99% of the energy of gamma radiation, having an incident photon energy of 4 mega electron volts. Sorry. Yeah. So for electromagnetic radiation of 4 MeV energy, the extinction coefficient for lead is given as 0.48 centimeter inverse. So any clue how to solve this? So again, it's the same concept that your energy is exponentially decayed with distance. So when you're dealing with an exponential decay, you have I is equal to I naught e power minus mu x. All your radiation are exponentially decaying with depth. So I is the intensity that is present at a certain depth, say x. I naught is the initial incident intensity that you gave. Mu is the extinction coefficient for a lead, and this extinction coefficient is constant for a particular material. So mu is constant, which is the extinction coefficient, and x is the penetration depth. X is the thickness. So you already have, so it is already given that 99.99% of the energy is absorbed. So what is left is 1 minus 0.9999 of the initial radiation. Since 99.99% of the energy is absorbed, whatever is remaining, that is what is I. It is not the amount absorbed, it is the amount remaining. So I is 1 minus 0.9999 of I naught. Hope this is clear. I is not the amount that is absorbed, I is the amount that is left. Incident intensity that is left at a certain depth. So if you substitute this value 0.0001 of I naught is equal to I naught into e power minus 0.48, which is your extinction coefficient, into x. So if you take a I naught gets cancelled, and if you take a logarithm on both the sides, ln of 0.0001 divided by minus 0.48 will give you the thickness of the lead. So this x is equal to 19.18 centimeters, which is your option B. Is this clear? Here you can see in every single slide we are dealing with an exponential decay, because that is how your your radiations are dissipated with respect to distance in the food. Any doubts in this particular problem? Okay. Moving to question 18. Which among the following as an entrainer helps in enhancement of phospholipids like phosphatidylcholine from dried egg yolk in supercritical fluid extraction? So you have dichloromethane, ethyl alcohol, tetrahydrofurane, and ethyl acetate. So any clue what is the answer? And what is an entrainer first? So entrainers are also called as often co-solvents, which will improve the solubility and the extraction of your desired solute. So apart from the supercritical fluid that you're using, let's say for example you're using a carbon dioxide as your supercritical fluid, you often add other solvents or other chemicals that will help to dissolve the solute better. So that is why you're adding entrainers to trap the no, it's not actually C. So it is used to trap the desired solutes. In this case, to enhance the solubility of the phospholipids and cholesterol as well, so ethyl alcohol is often used as an entrainer along with supercritical carbon dioxide. So carbon dioxide is often mixed with ethyl alcohol, and this helps in the enhancement of extraction of phosphatidylcholine, extraction of cholesterol, etc. Ethyl acetate is used with carbon dioxide to remove beta carotene, to solubilize beta carotene. And the other two, dichloromethane and tetrahydrofurane, are not used in the extraction of phospholipids because these are not as polar organic solvents as ethyl alcohol. So the answer is option B. So based on the kind of molecule that you want to extract, you will add it as a co-solvent to your supercritical fluid extraction process. This will increase the solubility and hence will increase the yield of your extraction as well. But while adding these entrainers, you should make sure that you should be able to separate it out of your solute. If you are trying to take out phosphatidylcholine, you have to add something that will be easily separated from the phosphatidylcholine and not contaminated till the later processes. So since ethyl alcohol and all are very volatile in nature, it is more preferred because further you can just use distillation or so to just remove the ethyl alcohol. Okay. So moving to question 19. The polarization effect of electromagnetic radiation causes dash heating: radio frequency heating, ohmic heating, microwave heating, and both A and C. So if you guys know what is the mechanism behind each of these heating, you will be able to answer this question. Yeah, the answer is option D. So both in case of radio frequency heating and microwave heating, you subject your food sample to electromagnetic radiation, and this polar this so you have the electromagnetic wave radiation that has very rapid oscillation. So what happens is all your polar molecules that are present in the food will try to align with the electromagnetic radiation that you are giving, and this electromagnetic radiation will be continuously reversing its direction. So you're having a polarizing effect of the electromagnetic field that you're supplying, and it will constantly reverse its direction. And because of this reversing of the direction, the polar molecules inside your food will also keep trying to align with the uh, continuously changing electromagnetic radiation that you are giving. So because the polar molecules are continuously changing, this will cause a kind of a heating effect, or this will cause molecular friction, and this will result in heating. So this is known as the dielectric heating, where your molecules will continuously reverse its direction to align itself with the electromagnetic field. So the polar molecules characterized in an electrical dipole moment will align themselves in the electromagnetic field. And since the electromagnetic field wave that you are giving is in rapid oscillation, the polar molecules will rotate continuously trying to align with it. This process is known as dipolar polarization. And as the field alternates, the molecule also reverses its direction to align itself with the field. And because of this, the energy is lost from the dipole by molecular friction and collisions. And this friction and collision leads to dielectric heating. And this is the mechanism behind both radio frequency and microwave heating. Whereas ohmic heating is more due to electrical resistance of the food. And it is not dielectric heating, it is electric. Ohmic heating is a different kind of a process. So the answer is option D. Hope this is clear. So since you are continuously oscillating the electromagnetic field radiation, your polar molecules will also continuously try to align itself, continuously reverse its direction, and because of so much stress, it will lead to molecular friction and collisions, and it will increase the temperature, or it will result in dielectric heating. Okay, moving on to the last question. A dose of dash kilograms is required for a 12D reduction of Clostridium botulinum. So any clue what the answer is? No, the answer is actually 48. A dose of 48 kilograms is needed for a 12D reduction of Clostridium botulinum. So Clostridium botulinum is one of the most toxic pathogens considered, because the toxin that it releases, even a small amount, is enough to kill people. So when you're dealing with food sterilization, it is extremely necessary to make sure that you do not have Clostridium botulinum inside your food sample. So you require a very high dose, since it's a very resistant bacteria also. It requires a very high dose of around 48 kilograms. But one of the disadvantages of using such high dose is that it starts to change your characteristic texture or flavor of your food as well. So such a high dose is not preferable in case of products, but that is what kills the organism. So if you feel that the kind of process that you're using is kind of affecting your food sample more, then you need to go for a different kind of a procedure, let's say thermal processing or so. So there is a fine balance between maintaining your food properties and killing your organisms, food pathogens that are present inside your food. So the answer is option D here. So this leads to the end of the session for this week. If you guys have any doubts in the previous questions, you can let me know. You can post it in the group chat right now, or you can post it, you can mail me, or you can post it in the discussion forum as well. I'll make sure that these session, both the recording as well as the PPT, is available to you as soon as possible in the NPTEL portal as well. If you guys are unable to access the NPTEL portal, kindly let me know.